correction, I'd like to back up just a little bit, because when I went back to the room, I was not happy with something because I was rushing. And I'd like to just go back to the aberration corrections for a minute, because the aberration corrector is important. And you remember this slide that I showed you before about the two types of aberrations. Yes, presentation mode. Just take a moment. Oops, back up. You remember this slide that I showed you a minute ago? I added some words well, over lunch. And I added this because when I was doing discussion, I was rushing, and I should have said I want to divide aberration correction into two regimes. One regime is before the specimen, and one regime is after the specimen, pre and post. Now, the corrections, the ideas are the same. We have spherical aberration and chromatic aberration, okay? And I was rushing through it, and so I want to just go over just a little bit more about the correctors, okay? So the first corrector that I talked about, this figure, I just added this small drawing. I want to talk about this corrector in pre-specimen. So if this is our entire microscope, I'm going to talk just about a corrector on the probe forming system, okay? And you see it here. So I'm talking about the ability to form a probe and to form a small probe. Now, this general curve that I showed you relates how we create a probe. And there are three limiting factors. There is something called the diffraction limit, the brightness of the gun, the spherical aberration, and the diffraction limit, okay? So one of which is how small of a probe can we form? It's called a Gaussian probe, D sub G. And that's related to the amount of current you want, the brightness of the gun, and that angle, convergence angle that we did. So that's one fundamental limit. You can't change that. The second limit is related to the aberration coefficients. It's also related to the angle of the beam, but instead of being linear, inversely to the first power, it's inversely to the third power. And it's controlled, this is just controlled by the gun itself. So this is gun related, this is lens related, okay? And there we have the angle of the beam and also this aberration coefficient, CS. And then there's finally something called the diffraction limit. You're forming a probe, it has a certain wavelength, and we have a certain angle, okay? So if you look at these three are shown in the three curves here. The blue curve there is the fact that you've got a probe of a certain beam current and a certain angle. And as the angle gets larger, we can make a smaller and smaller probe. So ideally, with a very large angle, the probe should be able to get smaller and smaller. However, because of spherical aberration is zero for very, very small angles, but it gets larger as we go up. So we have one coming down, the other coming up, and there's a relative minimum there, okay? And so this is only in the probe forming system, okay? So these are the three limits, the Gaussian or geometric limits, D sub G, the spherical aberration limit, and the diffraction limit. Generally, it's this one and this one that control how small of a probe you can get. So if we want to make that probe smaller, what can we do? Well, what we want to do is we want to get the probe as big an angle as possible, right? If this is the limit, the bigger the angle, the more convergent the probe is, more like that, the smaller the probe should be, except spherical aberration increases. So that's the limiting factor. So the whole idea of aberration correctors for the probe forming system is we want to make CS as small as possible so that this curve moves this way, and we can move it down and down. And what that does is if we can move this red curve this way, this minimum slowly moves this way, and our probe size gets smaller. All right. Now, and that's what I was trying to show you here. How can we make the probe smaller, well, we have to get rid of this. When we think of a probe, what we have to think about is, here's our electron beam, and there's a tail around it, okay? If I did a line scan through here, here's my probe. I'm making a line scan across here. We see we have a very sharp peak, but it's very long tails. You might ask yourself, well, what are the tails? It depends on the information you're trying to get. And we'll see later, if we're only worried about an image, we only worry about this information. If we're worried about spectroscopy or other information, where a few electrons create a lot of signal, we worry about something out here. So, do I want a very sharp, very intense probe? Well, this is a very sharp, intense probe. It'll give me a nice image. But the tails, this information out here, is a lot of signal which can create other images and actually complicate our images. So, ideally, what you want to do, you want to get rid of these tails. 2 ways to do it. Put a smaller aperture in. I put a smaller aperture in here, do a line scan through here. Here's my probe now. Those tails are now gone. But the probe is fatter. I make an even smaller aperture, I can even make it smaller. This is a sharper probe, but this is a fatter probe. Question, which one of these will give us the better information? Depends on the experiment we're doing. If all I'm caring about is an image, I'll go to this one. If I'm caring about doing high spatial resolution where all of the electron, I want to concentrate all the electron signal, this is the better probe. Okay. So I was trying to make that difference. Now, the other aberration is, and I added some words to this slide too, and a figure too, the post-specimen aberrations. Okay, so what limits, so one we talked about what limits the probe before the sample. What we now want to worry about is what limits the signal that we measure after the sample. Okay, so previously I was talking about these lenses. Now I'm talking about these lenses. I'm sorry I didn't explain that better earlier. All right, so we talked first about the illumination system. Now we're talking about the imaging system. All right, now this is the part that we have to think just a few minutes about. So this is our sample, there's our sample. So now I'm talking about what's happening here. So the beam comes in, hits our sample, and we get scattered electrons from here. These electrons go through lenses. These lenses have aberrations, okay? So we have spherical aberration and chromatic aberration going through the post-specimen lenses. Now, this is very complicated because there are multiple lenses here. Generally, what one says is when we want to interpret an image, what we're looking is we know what's coming in and we're measuring what's going out. Ideally, what we want is the structure of what's inside. And when we talk about imaging tomorrow, we'll talk about that. What I'm worried about here is, okay, this is what's coming out. That's great, but that's before I hit any lens. Now we have to go through the lenses of the microscope. So what we actually measure, psi, is not what comes out of the sample, but it's something that's multiplied by a function which we call the contrast transfer function. Okay, and I'll just call it T here. Okay, so this contrast transfer function incorporates all of the effects of all the lenses. In order to, ideally, this is what we want, but this is what we measure. So what we want to do is understand the transfer of information from point A to point B. Okay? Do we have, if anybody's here an audio expert, right? You know, audio systems, you have fancy amplifiers with lots of correctors like he has here, and you probably have better ones at home. All those things amplify and correct for the distortions of the microphones and the speakers. Well, this is the same thing. There's distortions in these lenses, and that's all described by this function called the contrast transfer function. Now, this is the slide I skipped. Oh, no, sorry, this is not the slide. So all of these lenses are all of the aberrations from all of the lenses after the sample are in the contrast transfer function, CTF. All right, now here's the complicated one. I was trying to avoid talking about this because it's a complicated equation. I don't want to derive this equation for you. This is the equation that describes the transfer of information through a whole series of lenses, okay? It's a mathematical expansion, let's not worry about it, but it's a function of many parameters. It's a function of the various aberration coefficients, it's a function of the wavelength of the electrons, it's a function of the focuses of the lenses, and it's also a function, and I apologize, but I've changed notation here, it's all a function of angle, okay? So what happens is this function is plotted here in blue, okay? And I'm plotting it as, this is the contrast transfer function as a function of resolution. All right. If you had no aberrations in a system and you put something out of the microscope, if there were no aberrations, it would come back, whatever here would appear here. That would be a contrast transfer function of unity. No losses. But in reality, because of all the terms in here, which consist of defocus, spherical aberrations. I use CS in the previous equations. Sometimes it's called C3 because it's the third order. And then there's higher order aberration coefficients. It's also a function of the energy of the beam, and it's function of the scattering angle, Q. Again, that should be alpha in the other curve. All right, so a perfect lens would have a perfect contrast transfer function. It'd be unity. In reality, it's never unity. For very low frequency, very large objects, an electron lens is pretty poor. It actually cuts off. The transfer is bad. Then there's a region where it's relatively high, and then it drops off again. Conventionally, the resolution limit of a microscope is usually defined at the first crossover of 0, this point right here. So how can we move this point this way? We move this point this way by adjusting the aberration coefficients, okay? So this is a contrast transfer function plotted for one set of coefficients. If I want to make this better, I want to expand this so I can get higher resolution, what do I want? I'd like to have something that's flat, and I'd like to have something that's flat to infinity. That'll never happen. But I want it as flat as far as possible, and I want that first 0, the first crossing, to be here. What do these oscillations mean? These oscillations mean the contrast in the image is changing. So let's pretend this is dark contrast, this is white contrast. So now I'm getting oscillating contrast. I don't want that to interpret an image, right? I want to have something that should be white always to be white, something that should be black to always be black. So we want this region as big as possible so it's uniform contrast, okay? So that's what the contrast transfer function tells us. And by adjusting, we can do this calculation by putting in the various parameters and see what value of focus, C1, what value of CS, which is C3 here, what energy of beam, so the wavelength of the electrons, and what scattering angle we need to move this as far this way as possible to get us the highest possible resolution and the flattest possible contrast. Okay? I'm going to skip that curve for a minute. We'll talk about it later. And this 0, this point right here, can be defined. We can set, when do I get a 0? Where's the first 0 of this? That's how this equation comes out. Setting that to 0, solving, we can solve and we can say that first 0 occurs when at 0.66 times CS to the quarter lambda to the 3/4. Okay? That's how this equation came out, by solving for where that 0 is. Okay? And again, in the previous equation, it was C3, here it's CS. Depending on who wrote the equation and when it was written, it's either C3 or CS, okay? Okay, so I just wanted to go back to that. And I've corrected it in the notes, and when you get the PDFs, it'll be corrected in there, okay? All right, so now I'm going to leave the instrument per se, and if this works, we're going to go to, where is this one? I hope this works. Yes, reminder, send your email information to Varun. All right. So up to now, we've only talked about an instrument. We've talked about sources, we talked about lenses, we talked about aberrations and deflectors and all. That's just to get you familiar with the machine. All right. I gave you a lot of information in, what, an hour and a half, 2 hours, maybe 3, I don't know. Very difficult to absorb all of that. That's why you're getting the notes. That's why you also have in the notes is my email address if you have a question. And I also give you the reference books to look at things. Now, let's change gears for a minute. We want to now actually look at not the instrument, but the information from the instrument. What information can I get about my material, whatever it is, to characterize it? Because that, remember the very first set of talks I gave, we have a problem, we want to get an answer. We have to ask ourselves, what kind of information is available? Now, there's two kinds of information. Well, there's 3 kinds of information that we can get. We get morphological information, shapes. That's an image. We can get crystallographic information. That'll be from diffraction. And we can get spectroscopic or elemental information. Okay, so that's the next 3 tasks. So this afternoon we're going to talk about diffraction. Tomorrow morning we're going to talk about imaging. And tomorrow afternoon we're going to talk about spectroscopy. Okay? So we're done with the instrument now. We'll probably say something about the instruments in between, and we'll go from there. All right. Now, there's lots of ways to talk about how a microscope gives you information. Some people start talking about imaging first, and then they go to high-resolution imaging, and then they go to diffraction. I'm going to do the inverse. I'm going to start with diffraction. Then we're going to talk about imaging and high-resolution imaging, okay? And then finally, spectroscopy. All right, why do I want to do that? Here is an image and a diffraction pattern, okay? Let's look at this first. What can I tell from this image? Well, I look at that and, okay, this is a hole, so there's nothing here. Good. There's something long and skinny, and there's something that's mediocre. Does that tell us a lot about the sample? No. It does tell us something about the shape. I have some long and skinny things in it. Something that looks like if you smoke a cigar. So what? Looking at this, I have a little bit of information that's solid. But if I look at now a diffraction pattern, let's worry about how I got it in a minute. I look at a diffraction pattern from M, I see a certain structure in that solid, okay? I look at the diffraction pattern from P, and I see it's completely different, okay? And you will see in a little bit that we can analyze this and tell something about what this is. This would be an FCC matrix. This is an M23C6 precipitate. I can measure the crystal structure. I can measure the lattice parameters. I can tell you something about this that I can't get from that simple image. So the message here is don't ignore diffraction. It is extremely powerful. It gives you a huge amount of information solid. It does take work to analyze it. It's a lot easier to look at an image and say, oh, I have a cigar and a flat thing. So what? Okay. Let's talk about now how can we get information out of that. And let's see, are we still in? Yeah, we're still in the right mode. Let's go forward. Here's another example of images and a diffraction pattern, both from the same thing. What can we tell about here? Well, we look at this and we see, oh, this area is a lot different. We have long skinny things, not quite cigars, and we got some flat guys in a matrix. And now we do diffraction from this, and what do we see? We have a diffraction, and this diffraction is telling us several things. We've got major reflections, which is mainly from the matrix, you'll see later. And we've got very fine detail in that pattern. Those come from the precipitates. And by analyzing the diffraction, we can tell what the structure of those precipitates are. Now, Hamish, who's coming in, he'll be here in a little bit, will be talking more about advanced on how to do some of that. I'm going to give you the overall view of electron diffraction, okay? Okay, so when we talk about electron diffraction, we've got a probe coming down, it hits our sample, and then there's electrons that are scattered. When I worried about doing diffraction, I'm not touching the condenser lens much, I'm forming my probe. My objective lens, which forms the first image, is running at constant excitation. And when I'm doing diffraction or imaging, what I'm doing is I'm varying the final lenses of the microscope, what's called the diffraction and intermediate lenses. Okay? So if I draw the optics of it, so our sample's sitting there, okay? We have a series of lenses after the sample. So we've got the objective lens that surrounds the sample. That's basically here, it's the objective lens. The objective lens doesn't change when we go between imaging and diffraction. It stays constant. It has two characteristic planes. It has an image plane and a back focal plane. Okay? When I want to get an image, what I have is I adjust the post-specimen lenses to take that plane and move it down to my screen. That gives me my image. Objective lens doesn't change. When I want to get a diffraction pattern, all I do is I change the strength of this lens, the intermediate lens, or it's sometimes called the diffraction lens, and instead of looking at the image plane, I look at the diffraction plane. Okay? And now I have a diffraction pattern there. If I want to magnify something, I don't adjust this lens, because this lens is looking either at the image or the diffraction pattern. I adjust the lenses after it to give me a bigger image or a bigger diffraction pattern. Okay? So when you push a button that says D, or diffraction, all you're doing is adjusting this first lens to look at either the image plane or the back focal plane. When you turn a knob that says magnification, you're adjusting what's called the projector lenses, the final lenses, to give you a magnified view of what's ever at the next plane. Okay? All right. What's special about electron diffraction? Let's talk about that for a minute. Okay. It's one of the, to me, it's one of the most important features of a TEM. Okay? It gives us the ability to determine crystallographic information about the sample. We can determine orientation, we can determine lattice parameters, we can determine structure. Okay? Using diffraction, we can answer simple things. Is a sample crystalline or not? Yes or no? Okay? Crystalline meaning an ordered structure of something versus amorphous. I keep turning that on. I shouldn't touch the screen. I'm too used to it. If it's crystalline, can we determine are there characteristics? The answer is yes. You'll see that in a little bit. Is it monocrystalline? We'll show you that. And what's the orientation of the specimen relative to everything else? Okay. And other question, is there more than one phase present? Yes or no? Okay. So to understand diffraction, we have to go back to a little bit of physics. And the first thing I want you to think about is I've got a single atom sitting here in free space. Okay, and I'm going to hit it with an electron beam. Okay, so here's my single atom. Electrons are going to hit it and they're going to scatter. And they're going to scatter with different angles. First thing what you need to know is the intensity of that scattered radiation from a single atom goes as the square of the structure factor, F of theta. F of theta is a function of the material we're looking at. Okay? It's a function of the energy of the beam. It's related to the beam. It's related to the wavelength of the electrons. Okay? It's related to the atomic number of the atom. Okay? And it's related to the angle that we're measuring. So, what's the first thing to? High Z materials have high scattering. Low Z materials have low scattering. So if we just compare intensity now. Remember, the intensity is the square of this number. So high Z, gold, high intensity scattering, low Z, aluminum, low intensity scattering. There's an angular dependence. Higher Z materials scatter to higher angles, lower Z materials scatter to lower angles. All right, so you can write this down, and that's fine. But in the real world, you never look at a single atom sitting in free space, right? You could. I mean, in principle, you can get a single atom floating across your screen and grab a diffraction pattern from it. Difficult, but not impossible. In the real world, what we usually have is a collection of atoms. Okay? They're collected into some sort of structure. It may be a liquid, it may be a gas phase, it may be a solid, but they're a collection of atoms. And if we have, and I'll call this collection amorphous for the moment, meaning that there is no structure, the atoms are just jumbled together, okay? That intensity distribution that we measure as the electrons go past that collection of atoms looks very similar to what we had. Remember we said for a single atom it was just f of theta squared. However, as soon as we put those atoms together into some sort of collection, there's a multiplicative factor in there. And that multiplicative factor has to do with the average interatomic spacing of the atoms. The more atoms they are, the closer packed they are, the more scattering you're going to get at a certain angle. So, if we were to look at a diffraction pattern, is there going to be some scattering distribution? The answer is yes. And remember, for a single atom, it just monotonically decreased. It's no longer a monotonic decrease. There's now a sinusoidal variation. And that sinusoidal variation is a function of the diffraction angle that we're looking at, and importantly, the average interatomic spacing of those atoms. So if I have my diffraction pattern and I measure a line profile through there, I can get information about the average spacing of the atoms in my solid. Okay. So that's, okay. Yeah, so I've just drawn you, here's my amorphous solid. This happens to be an example of amorphous silica, doesn't really matter. The atoms are arranged in some way. We've got a diffraction pattern from it. You notice we no longer have a monotonically distinct, this is a real diffraction pattern now, okay? If I did a line profile through there, I'm going to see an oscillatory structure. By measuring the periodicity of this oscillation, I can determine the mean or average atomic spacing in the solid. Okay, let's go a step further. Let's take our disordered solid, this jumble array of atoms, and let's start adding some sort of ordering to it or periodicity to it. So a perfectly random distribution will look something like this. As there begins to be some ordering, okay, what will happen is these, how should I call it, broad, diffuse rings will begin to coalesce. They will narrow. They will segregate. You notice this one, for example, was fairly wide. It's now broken up into two, okay? Done it again. I have to learn not to touch that. What's happening here? We've gone from a random array to a collection of finite. If we take our material, and so now I've drawn, this is an example of a nanocrystalline film of palladium, okay? We saw it's still rings, okay? If I let that film grow so that the grain size starts increasing, what's happening is that those rings start breaking up into spots, discrete spots. And if I let that grow even further until I get a single crystal, now those discrete spots come into a single array. So we've gone from an amorphous to a polycrystalline to a partially single crystal to a single crystal pattern. So these are the typical types of patterns that you would see in electron diffraction in a microscope, depending on what you're looking at. Let's see now. I think I will skip this slide. Okay. Let me give you a real example of that now. Okay. Here's a material that I have intentionally taken from an amorphous state to a crystalline state. So it's all one sample. We amorphized this area, and we left this one polycrystalline. Okay? If I take a diffraction pattern from here and compare it to a diffraction pattern from here, this is exactly what we see. Okay? So this is the diffraction pattern from the polycrystalline area. This is the diffraction pattern from the amorphized area. What do we see about this? Well, we see these very broad rings, and when what's going to happen is when the material crystallizes, we form the atoms that correspond to this general spacing start to order, and we form very discrete crystalline bands. Okay? And what I've shown you here is a simple line trace through there and a simple line trace through there, and you see that here. The polycrystalline area and the amorphous are the irradiated area. Okay. The way we made this amorphous is we irradiated it with high energy ions. That's irrelevant for what we're talking about here. Okay, so in order to talk more about diffraction, I have to mention a few things about crystal structures and crystals. Now, I'm going to say just a couple of slides about crystal structures and crystallography. That's a whole series of lectures. I'm not going to cover that. There's no way I can do that. But what we can say is when we have a periodic arrangement of atoms, where they're periodically arrayed, we call that a lattice. Okay? That lattice, that periodic array, can be arranged into something called a unit cell that describes the solid. Okay? What's on the next slide? We can describe the atoms in that solid by radius vectors and certain directions, A, B, and C, crystallographic directions. We can say the solid can be described by a unit cell, and that unit cell has parameters. It has lattice parameters in multiple axes. Okay? There are lots of different types of crystal structures, going from simple cubic to tetragonal, orthomic, triclinic, rhombohedral. I don't have time to talk about it, but you should know they exist. The references that I gave you have references on electron diffraction. And you should know that there are, in general, 7 different crystal systems with 14 different Bravais lattices. Why am I bringing all this up? Because when Hamish gets up to talk about advanced electron diffraction, he's going to be bringing up crystal structures and diffractions and Bravais lattices and the like. So you should know they exist. You should know that it's a lot of work to make sure you understand this correctly, and it's not something that we can cover in a lecture like this today. Okay. That should be a proper course in electron diffraction. Okay. The other thing to realize is that when you have crystals, crystals with a very specific structure, we can describe those crystals as having planes of atoms. I'll talk about planes quite frequently. I'll say this is a 110 plane or a 111 plane. That has to do with the description of where that plane goes through that crystalline lattice. Okay. Again, if you've got a question on that, let's talk about it later. But I will mention crystal unit cells. I will mention directions in the crystal. I'll frequently talk about A, B, C, or X, Y, Z. Those mean the 3 principal directions in the crystal when it's a periodic lattice. And I will frequently talk about different types of planes. For example, if I'm talking about a face plane, let's assume I have a simple cubic system. I'm talking about a face plane. Well, think about it. If I've got 3 axes, X, Y, there's the X-axis, the plane on the X-axis. There's a plane on the Z-axis. Do I have the Y? Oh, yeah, there's the Y. So there's the Y, the X, and the Z. You can see we have periodic planes. I can have diagonal planes. I can have planes going across the corner. So all of these relate to the crystal structure of the solid. I apologize for trying to give you all of crystallography in about 5 slides. But I need to make sure that you know what I'm talking about when I say, I'm talking a 111 plane. It means a plane going through the crystal structure along a certain direction, or a 100 or whatever. Okay? You will hear similar notation when Hamish starts talking. Again, a good crystallography course, a good X-ray diffraction course will cover everything you need to know about. Well, no, probably won't. It'll cover some of the things you need to know about crystallography. Go forward. Uh-oh. It's stuck. Why aren't you moving? Uh-oh. What are we getting? Okay, you will frequently hear me talk about planes, HKL meaning alpha, XYZ, nomenclature. And I don't know where HK and L came from. I don't remember that. It's always been HKL, and I don't remember why. We frequently have notations. The standard notation is when it's a bracket like that, we're talking about a plane. When it's a curly bracket, they're equivalent planes. When it's a square, that's a direction. And when it's a pointy direction, it's equivalent directions. So just notation. You'll see these kinds of notations on a lot of the slides I'll be showing in both the diffraction and the imaging. So just so you know where it comes from. All right, let's go back to diffraction now. I think most of you have probably done something called a Young's fringe measurement, okay? So what is a Young's fringe measurement? What you have is a plane wave of radiation, usually a laser or a light source. It hits an array of slits, right? And some kind of slit array. The waves that come through interfere. At a certain plane, we get an interference pattern, and it'll look something like that, okay? That's Young's fringe experiment. All right? Electron diffraction is the same thing. The only difference is that we replace the slits by an array of atoms. And the diffraction effect is, in effect, the diffraction between the slits formed by the periodic array of atoms. So if you think of an interference phenomenon, that's what diffraction is. It's interference where instead of an array of slits or holes, what you have is an array of atoms. And it's the periodicity of the atoms gives rise to the interference phenomenon. So let's show you that in a different way. So now here's our array of atoms. They form planes, okay? And we have planes in the crystal. So here are two equivalent planes. Pretend they're the two planes here. We have an incident beam of radiation, which in this case happens to be electrons. But the electrons can be treated either as single particles or they can be treated as a wave. Okay? It's the wave-particle duality. We're not going to talk a lot about that. That gets us into the realms of philosophy and physics. Okay? So when we have a incident beam, plane wave coming in, interacting with planes, those incident beams can be diffracted according to Bragg's law. Do I have it on here? Yeah. They can hit the planes, be refracted, and come out. What we want to do is we want to look at the path difference between PO and D. POD is equal to n lambda times 2d sine theta. You can just work it out from simple geometry, okay? You know the wavelength, you know the angles, you know the d spacing. That's the equation you get. That's the famous Bragg's law for diffraction, okay? And we get constructive and destructive interference, and we get what's called a diffraction, a pattern at this point. What does a diffraction pattern look like? Here's a diffraction pattern from a periodic array of materials, okay? We've got major Bragg reflections, okay? Because this is a two-dimensional ray, unlike the slit pattern that I showed you a few moments ago, which there was only one. Let's go back up. Let's back up. Yeah. Here, I only had a single dimension array. I only have a line of diffraction. If I had a three-dimensional array, I would have multiple arrays of diffraction, of interference, sorry, not diffraction. So this is a diffraction pattern from a periodic array in 2 dimensions. So I don't have just a single line, but I have an array. And you see, this one's actually pretty complex because not only do I get major reflections, I see a lot of minor ones. And we'll talk about that in a few minutes. Okay. The major reflections occur at characteristic scattering angles. The intensity of the major reflections now is determined, remember the equation I showed you before, it was little f times theta. Okay. Now that intensity is proportional big F times theta. What's big F? This is really now what I call the structure factor. There's the atomic scattering factor that we had before. This is an expression that reflects the periodicity of the atoms in the solid. Okay. All right. So the intensity we get is the square of the structure factor, which is the square based on the sum of the squares of the individual scattering factors times the periodicity function. This periodicity function is related to the interatomic spacing in the solid. Okay. Okay, what kinds of diffraction patterns can we get? There's several times. We can get the ring pattern that I showed you, a spot pattern, and then something called a Kikuchi pattern. The ring pattern comes from either polycrystalline or amorphous samples. Okay, we'll talk about those. Spot patterns, nice clear discrete spots, usually come from single crystal regions of a solid. Okay, if you have an area that has two different single crystals, you'll get two overlapping spot patterns. You'll see that in an example. B and C, spot patterns and Kikuchi patterns, are often in the same pattern, in the same measurement. And you'll find, we'll show you in a few minutes that the Kikuchi patterns happen from very thick samples. The spot patterns happen from everything. Okay. Kikuchi patterns are due to inelastic scattering of the electrons. Spot patterns are mainly the elastic scattering. Okay. Ring patterns, the most useful thing about ring patterns is the identification of phases in polycrystalline materials. Okay. Okay, so let's look at that first. So here's a ring pattern, or a polycrystalline pattern. Why did I immediately say polycrystalline and not amorphous? First thing I looked at, I can look at this pattern, and what do I see? I see very sharp rings, not broad, diffuse rings. If it's broad and diffuse, it's generally due to disorder in the solid, so it's an amorphous material. When the rings are very sharp, so these are the broad diffuse rings that we had. These are the very sharp ones. When they're very sharp, it's usually a polycrystalline material. The important thing to notice, remember, just as I told you that the periodicity of the diffuse rings was related to the spacing of the atoms, the periodicity of these rings is related to the crystal structure of the solid. Okay? Let me show you an example of that. Here's titanium oxide in three different phases: rutile, anatase, and brookite. It's polycrystalline. We've got ring, and I've just chopped the pattern up into different things. And what you see are there's rings everywhere, and the rings change. They change because the crystal structure changes and the periodicity of the atoms changes. Okay? Can we analyze this? Yes. The way we analyze it is by measuring the spacing of the rings. Okay? How do we do that? We do something very simple. Okay? What we do is we're looking at a diffraction pattern. We can come back and say that diffraction pattern is due to a Bragg reflection, so either a beam is coming straight through, the straight through beam, which is that guy right in the middle, or it's due to a beam that's become diffracted and come off at an angle. One of these. Okay? So what do we need to know? We need to know a few things. We need to know what the radius of that ring is, there to there, or equivalently, what I usually do is it's hard to measure a radius, it's easy to measure a diameter. Okay, why is it hard to measure a radius? Because it's usually pretty hard to find the center. This is usually very bright. So if you're doing a diffraction analysis, what I always do is measure a diameter. It's easy to find the biggest diameter. And I'll make a table of diameters. What we can show, and I'm going to draw you now a simple illustration of that diffraction event. We have a diffraction event that happens here. The beam comes down and hits the film or their detector, and there's a ring at a certain radius. I can draw this geometry out, and I can tell you that this forms a relatively simple geometric triangle, okay, where the radius, the length of diffraction from where the beam hit the sample to where it hit the screen, and the radius are very characteristic. That radius is proportional to 1 over the diameter of the spacing of between the planes. This length is proportional to 1 over the wavelength. Okay? If we take that geometry, we can show that the very simple equation describes it, namely the radius times the d-spacing is equal to the length times the wavelength. This is called, sometimes L is called the camera constant of the microscope, or camera length of the microscope. That's where the L came from. Lambda, the wavelength, is the wavelength of the electrons. R is something you measure. D is the d-spacing. So how do we use that to measure something? We have a diffraction pattern sitting there. We have an unknown. If I know lambda, and if I know L, all I have to do is measure R, and then I automatically have D, the d-spacing. All right, so you put your sample in, you know the wavelength of the electron. Why? You know the accelerating voltage. I gave you the formula for calculating the wavelength. You look up on, somebody tells you, here's the camera length, and you've got the d-spacing. So what did I just go wrong there? Somebody just told me what the camera length is. Don't trust it. Okay? So what you're going to do first is to calibrate. Exactly. Good. So how do you calibrate? You get a material that you know. Get yourself, you can easily buy polycrystalline gold, polycrystalline aluminum, some sort of a material, pure element that you know the d-spacing for. Okay? So what we're going to do is we're going to put in a material that we know. This is an example from aluminum. I can look up in all the good books the lattice parameter for aluminum. I can calculate, knowing the lattice parameter and the possible reflections. Again, this means you know crystallography to know this. But I know that I'm going to have the following lattices in aluminum: 111, 200, all of these. These are the lattice descriptions that I know. I know the lattice parameter of aluminum. I can calculate what the d-spacing is using this formula. There's the d-spacing. I can go to my aluminum pattern. Because I know my crystallography, I know 111 is going to be the first ring, then 200, 220. I can measure each of these rings. So I know the d-spacing. I know the radius, R. I've measured that in all of them. And I can calculate the camera constant, R times D. Okay? So I take R, I take D, and I calculate the camera constant. Notice it's nearly constant. It should be. All right? What's going to change? What will change is if I go to a different accelerating voltage or a different camera length. But that's now a constant. I've now calibrated my instrument for the conditions I've got. That's the magic number. All right? Now I'm going to go to my unknown sample. I think that's the next one. Yes. So this is one. I happen to know it was gold, but that doesn't matter. I put it in under the same conditions. I have my camera constant that I measured before. I measure my R's. From the R's in my camera constant, I can calculate, here's another camera constant. I can calculate the spacing. Okay? So that's how you would do a simple analysis of diffraction for ring patterns. Okay, what's nice about these? Well, the ring patterns is characteristic of the planes of the crystal. It's, very importantly, it's calibrated for the magnification of the camera length you did. Most microscopes will allow you to change camera lengths, so you can make it bigger or smaller. You need to calibrate all of those. Another important thing. I'm going to go backwards now a few slides. This one. One of the things that's very important is this distance, the camera length. Now, you might think, what are the kind of camera lengths I work with? The camera lengths are typically hundreds of millimeters to thousands of millimeters. Okay, that's very important. But all of that assumes the lenses are working the same every time. It also assumes the sample's always at the same spot. Okay, so there's something called setting the eccentric height of the microscope. Who's ever training you on how to use the microscope will show you how to set that. You always need to make sure the sample's at the same position. You don't want it too low or too high, because that will slightly change the camera constant. It'll change the length. How much of a change is it? It depends on how much variability you have in your instrument and what camera length you do. You need to make sure you're always at the same conditions. Okay. Let's go forward. So once you've calibrated it and you know the camera constant, L, you know lambda and you know R, then you automatically have D. All right. Now, a simple set of formulas. You can look these up in all the good books on how you interpret the D spacing relative to lattice parameters and crystal structures. I'm not going to have time to talk about that, but this is all in any of the good books on X-ray crystallography, X-ray diffraction. You can look that up pretty well. All right, we've gone through this one already. Let's see what's next. Oh, that slide's repeated. That or I'm going the wrong direction. Ah, yes. Now I see what I wanted to do. All right, so this was an example of polycrystalline material. What happens when we go from polycrystalline? How did I know it was polycrystalline? Remember the sharp lines? Tell me. What happens when you go from polycrystalline to a single crystal? Okay. So I'm going to show you the same material first as a polycrystalline, and now here's the same material as a single crystal. What's happening? These individual rings are breaking up, right? The grain. The reason we have a ring is because we have lots of small grains, each of a slightly different orientation, and they're rotated, they're mismatched. If we let those grains grow, or actually have a single crystal, what's going to happen is instead of having rings, we're going to have individual diffraction spots, okay? And you can see how these overlap very precisely with the various rings. Okay, so when we go from polycrystalline to single crystal, that's what we get, okay? The same principle holds for measuring the D spacing here. You've got the camera constant, you've got the wavelength, you measure the distance, you can tell you what the D spacing is for that particular reflection, okay? So what do I have here? So how do you index simple diffraction patterns? What we do is we use the camera constant method. We make a table of diffraction spots, and from that table of D spacings, we can look up possible crystal structures. Now, why do I say make a table? Because it depends on what you're looking at. This is a collection of diffraction patterns, all from the same material. Okay? They're all from silicon. They're all from a camera length of 470 millimeters. Okay, but they all look different. And they all look different because this is a single crystal, and we're going down different crystallographic directions from, let's see now, that's a 110, that's a 100, that's a 111. What's this one? Let me look at it closely. 112. No, that's a 112. Now, you notice I'm looking at these, and I can almost index them just by looking at them, and I'm doing that by symmetry, okay? Because I know what this looks like. Look at this. This looks like, okay, let's start here. That's a nice square. Silicon is an FCC. That's a cube looking down the 100 direction. This one, if you look at it, it's a hexagon. I'm looking down a 111 direction. I'm looking along a diagonal. This one is a squashed hexagon. Okay, that's a 110. Okay. Now I can do that because I've been looking at these for years. Okay. We can nicely, if you want, measure the spacings using our camera length constant and make a table. And we said, these are the D spacings I see in this pattern. These are what I see here. These are what I see here. And then you can compare it to a table of numbers. So this would be a table of numbers that we can make and say what sort of HKL indices they are, what index they are, and whether we see a reflection or not. Using those, we can determine something like this. So here is, again, silicon. We've got a nice squashed hexagon now, right? You see the squashed hexagon. I can measure, let's see now, I think the next one shows me, yes. Let's do this, yeah. So I measure the distance between those two, I call it R1, R2, R3, I can measure those distances. I can look at the ratio of R1 to R3. I can then say which of these are allowed reflections. I'm going to go backwards now. We're looking at these, and some reflections are allowed, some are allowed, and some are not allowed, depending on the crystal structure, whether it's an FCC, a BCC, or diamond. Okay? And then from that, I can determine a ratio, and then from that, I can determine what the plane is. Now, I showed you that very quickly. The only way to do this is to sit down and do it one by one. Okay? But that principle is there. The other thing that happens is when I look at diffraction, I can relate diffraction patterns to crystallographic directions in the solid. So I'm looking at, for example, the cube zone, 001. How many of you know what a Wolf plot is? Did anybody know that? If you had any, who's had X-ray diffraction courses? Anybody one? You know what a Wolf plot is, right? Okay. Think of the Wolf triangle or the serigraphic triangle. This is the serigraphic triangle that you would see in normal diffraction. We go from 001 to 011 to 111, and we go along different reciprocal directions. We see the patterns changing very symmetrically. Okay, now that's a pretty complex structure. That's because this is not simple silicon, but rather an ordered BCC. The other thing to realize is that the diffraction pattern and the real space image are reciprocals to each other. Okay? When you're looking down a cube axis, it doesn't matter. If it's a cube, it's a cube. But when we look down the 011 axis, for example, the pattern is short this way and long this way, and it's the opposite in real space, because the diffraction pattern is reciprocal to real space. And here's the 111, always looks the same. It's always symmetric. You can cheat. You can look it up in a book. Okay? Or you can do it by eye. There's also a bevy of computer programs that'll calculate what diffraction patterns look like for you. Okay? I would, if I were you, I would learn what the diffraction patterns for your systems look like. If you're always working with FCC, learn what FCC patterns look like, BCC, orthorhombic, tetragonal, whatever it is. You should learn to recognize what the patterns are, because you'll be seeing them a lot. And it's a lot faster to be able to recognize and look, oh yeah, that's a 110 or that's a 111. And remember, the different crystal structures have different shape patterns. Now, in addition to a regular array of spots, when your sample has a finite thickness, you will see what I call regular diffuse scattering, and you will see a bevy of dark and bright lines going through your diffraction pattern. These dark and bright lines are called Kikuchi lines. After Kikuchi, the guy that first not discovered them, he described what they were. Okay? And these lines are elastic diffraction of inelastically scattered electrons. So what's happened is electrons comes in, it's lost energy, it's become inelastic, and then it Bragg diffracts. So what's happening is an instant electron beam comes in, it hits an atom and scatters, loses some energy. Some of it goes forward, some of it goes off at an angle. Those inelastically scattered electrons also hit the Bragg planes, and they get diffracted. The difference is they are tied to the crystal structure of the solid. And what will happen is, oh, you see it here. We have the dark and bright bands corresponding to whether it's a short diffraction or a long diffraction. White lines versus a dark line. Okay? This is a very thick sample. It's so thick that we can't even see the Bragg reflections anymore. We can't see those bright spots. But the Kikuchi lines are still coming through because they're diffraction of inelastically scattered electrons. When it's very thick, you have a lot of inelastic scattering. When it's thinner, we have a combination of both. When the sample is very thin, you get no Kikuchi lines, you just get the Bragg reflections. These are very useful. They're very useful because for me, I use them as a roadmap. Okay? I'm going to show you now. This is a Kikuchi map. Okay? Something I created back in 1978. It's an experimental Kikuchi map. Each one of these squares is an individual diffraction pattern. So you say I took a lot. I took my crystal and I started at 001 and I slowly tilted it and took a photograph of each thing. Why did I do that? Because now look at the map that I've produced. I can, using my Kikuchi bands, travel. Oh, I know I'm at 001 and I happen to want to know I want to do a crystallographic experiment and I want to go to the 111. I can look at this map. The spacing of the Kikuchi bands is proportional to the despacing of the lines you want. The direction is proportional to where you want to go. I want to go to 111. I can look at this pattern and say, oh yeah, I want to go that way. And I can just travel along that Kikuchi band all the way till I hit the 111. Or, if I don't want to go to the 111, but I want to go to the 112, the 113, the 114, I can go across that. Or I can go from 001 to 001 to 011, or I can go to 012, 013, 014. Now, who caught what I just did? I did simple vector math. Okay? I know that's 001. I know that's 011. If I do a simple vector addition between those, I'm going to get that point. What's it going to be? That's 012. I'm going to vector math from this one plus this one. I'm going to get that 013, 014. Similarly, we can go along here. From there to there, the first major one is 112. So that's 111 plus 011, 112, 113, 114. We can go vector math in here. Very simple way of indexing your pattern. More importantly, it's a roadmap of your crystal. You will, depending on the kind of question you're asking, need to go to different directions in reciprocal space or in crystallographic space to analyze an image. If you have a Kikuchi map in your pocket or on the wall or in your head, you can travel around reciprocal space to go to very specific directions in crystallography without spending a lot of time trying to figure out where you are. And again, that's an experimental one. People publish them too. And you'll notice that looks very much like what I just showed you. There's the 001, 011, 111, okay? This happens to be for an FCC system. They're again slightly different, BCC, HCP, whatever, okay. How did we do that? One thing I didn't talk about when we talked about the microscope is the specimen stage. You put a sample in the microscope. How did you do that? You put it in some kind of a holder, some way of holding it and putting it in. Not only does that holder allow you to insert a sample into a vacuum system and move it around, X, Y, Z, it also allows you to do tilting. Okay? There are a whole variety of different holders depending on which kind of microscope you have. Some holders are single tilt, only tilt one way. Some are double tilt, so they allow you to tilt one and then a second. Other ones do heating, cooling, or whatever. Because this is you've got the Thermo Fisher Titan downstairs, you have what's called a single tilt holder, so there's only one sample holder. There are some microscope manufacturers. This is from these are JOL systems, I think. They have two holders. Most people just use one nowadays. It used to be, well, we'll load two so we can load two samples and look at two. Very few people do that anymore. All right, so we talked about apertures. Is that the right slide? Yes. We talked about apertures before, and we talked about apertures doing two things: controlling the beam current, controlling the coherence. But in diffraction space, they also control something else. They control the angle of the beam and the angle that we see in the diffraction pattern. So it's going to go back to our very first image that we had before, where I had the cigar-shaped guy. And if you notice this diffraction pattern, those diffraction spots aren't nice small pinpricks, they're disks. And the reason they are disks is because my beam was focused down onto the sample. In order to get pinpoint diffraction, we have to have a parallel beam of electrons hitting the sample. Okay? When that happens, in the back focal plane, the electrons are focused to spots, very small spots. If we have a convergent beam focused on the sample, those spots become disks. Okay? Typically, as soon as you see a disk, you say, it's still a diffraction pattern. We tend to call it a convergent beam diffraction pattern rather than a parallel. Why? Because the beam's converging. Very simple. Okay? How different can it be? Here is the same sample, same area of the sample, one with a near parallel beam, notice the small spots, and one with a convergent beam. All right, now let's look at these two because I want to think about it for a difference. So one's with a parallel beam, one's with a convergent beam. That's the parallel beam, that's the convergent beam. These two spots are these two spots. Okay? Where's that guy? Is it there? It's there, you just can't see it. Why? Because that intensity is now spread out into a very large disk. So it's very weak. If we did a really long exposure, we would see a large diffuse, in fact, a spot this big, roughly right here. Okay? See that guy? Is that guy? Notice how big he is? Notice very interestingly, there's a lot of other information hidden in here. Okay? Is that information here? Absolutely. We don't see it. Why? Because the intensity is so weak. So what is the advantage of convergent beam diffraction? A, you have a smaller beam. B, it reveals additional information about the solid. Look at very closely at this diffraction spot. See all these lines in here? We'll talk about that, and Hamish is going to talk more about it when he gets here. Look very closely. Sorry, the exposure isn't right, but you can see some of this information just barely in there. It's actually all of this information here is here. We just can't see it because it's not illuminated. So how do we go between parallel illumination and convergent beam illumination? You do that all with your probe forming lenses. Okay? And remember, I told you about focusing your beam down on the sample, and then in order to get a more parallel beam, what do? You have to under-focus the beam. So you have to weaken the lens. So when it's focused here. When I weaken the lens, the focal point moves down. The more I weaken the lens, the more parallel the beam becomes. Okay? Remember that. And ideally, when it's as weak as possible, I have a parallel illumination of the sample. Now, there's another consequence of making the beam more parallel. It gets bigger. Okay? For a given aperture size, the aperture isn't shown here. For a given size aperture, the beam is a certain size. If I want to still have a parallel beam but have a smaller beam, what am I going to have to do? I have to put in a smaller aperture. When I put in a smaller aperture, what happens? The intensity drops. Okay? All right. Select area diffraction is a methodology by which we can get a diffraction pattern from a certain area of the sample only. Okay? If I put a beam down on the sample and there are a lot of grains all over the place, I'm going to get diffractions from everything. Ideally, I would like diffraction only from one spot or one interesting area. How do I do that? Well, there's two ways of doing it. Today, most people just focus the beam down to a certain spot. That's actually probably the best way today on how to do it. Focus your beam down. Yes, you will get a partially convergent beam pattern, but you can still analyze it. In the past, we used a technique called select area diffraction. And in select area diffraction, what you had is you have a virtual aperture that's illuminating an area of your sample. Oops, no, now I've done it. Hang on. Which one do I push to get it back? This one? Nope, that's not it. That one? Nope. That one. Ah. Ideally, what we'd like is a nice parallel beam hitting, I keep touching the screen, hitting our sample. We can't put an aperture directly on top of the sample. Usually we want a very small area. So what we do is we actually put an aperture further down in the electron optical column, down in the lens stack, and that aperture projects backward to a small area on the sample. It gives us a limited diffraction pattern. Does it work? Yes. Has it been used routinely for years? Yes. The limitation is there's only a certain size area that you can define with that. Again, what causes that limit? Aberrations in the lenses. So can we insert an aperture and define an area on the sample from which to get a diffraction pattern? Yes. On a good day with the wind blowing right and the phase of the moon in the right quarter, you're getting half a micron or so. Okay. That might be good enough for your experiment, but it may not. Most of the time today's it's not. The alternative is just to focus the beam down. I have not done select area diffraction in decades. Okay? I've used focus probe, I've got a convergent beam pattern, and the modern microscopes, particularly those with corrected optics, can give you very small parallel beams, as small as 100 angstroms, and it still be parallel. So I don't need select area diffraction anymore. The instrument you have here is not a probe corrected machine, but an image corrected machine, but you'll still be able to get a small probe. I don't know exactly which lenses you have or how small you can get, but it depends on the lens, the number of lenses, and the sizes of the apertures. But certainly 1,000 angstrom probe will be easily done on the machine here. All right, let's move forward. Yes, we got that already. All right. Why do I want to do convergent beam diffraction and not just always do select area diffraction? Well, I already mentioned this already. There is an aberration because of the aberrations of the post-specimen lenses. If you don't have an aberration corrector, there is a certain minimum area that you can see, and that's related to the angle of scattering that you get, the Bragg angle that you're looking at, and the aberration coefficient, CS of the lenses again. That defines what the minimum size you can see is. As a result, half a micron on a good day with the wind blowing right is about what you can get for select area diffraction. If that's good enough for you, select area diffraction is fine. There's nothing wrong with it. In the real world, nowadays, that's pretty big, half a micron. And we want to do, 1/10 of a micron or smaller. So what we want to do is instead of going with a parallel beam, we're going to focus our probe down. And here we have the advantage of controlling forgetting about overfocus regime now. We're either going to have a focus probe or an underfocus probe. Okay? The more you underfocus the probe, the more parallel, the smaller that angle gets. So you can get near parallel illumination or close to it with a probe forming system. So select area aperture isn't really too keen. Okay? Another example, we've seen this one several times, but now what I'm showing you is an example of going from same system now. All I'm doing is changing the focus of the lens. I'm going from near parallel illumination to slightly convergent, 10 to the minus 3, to 10 to the minus 2, 1.6 times 10 to the minus 2 to 2.6 to the minus 2. Notice how these discs are getting bigger. Remember those very weak spots that we saw before? You can see them here, where I'm just starting to spread them out, okay? And at this point, they're no longer visible, okay? We see some distortion here. That's probably because I haven't focused things, okay? Nicely. One of the things that Hamish is going to talk about when he gets here, which I expect soon. Is he on his way? Yeah. Good, because I'm getting tired of talking. Yeah. Well, we just have a little bit more, and then we'll stop, I think. Let's see, how many? I think we have a little bit more. Well, let's see. We've only gone for an hour. We can go a little bit longer. But I'll need to stop talking a little bit. Hamish will be talking about the information in convergent beam patterns, okay? This is a beautiful convergent beam pattern from M23C6. Notice what's very important in this pattern, and again, Hamish will talk to you. We have some reflections that are very dim and almost blank. other ones that are fully excited, some that are in between. We can look at complex. This is now all silicon. There's a nice parallel pattern. And now I'm going to go to convergent beam mode, and that pattern becomes that pattern. And now all I'm going to do is I'm going to keep my convergent beams fixed. I'm going to change the thickness of the crystal. So all I'm going to do is move the probe to a thicker area. I go from this to this to this to this. Do you see the pattern here? Okay? You see the structure of this changing? What does that tell you? If I know that periodic change and I can measure it, I can measure the thickness of my sample. Power of convergent beam diffraction. Not only do I get the d-spacing, I can also measure thickness of the sample. This information, by the way, for those of you that are really interested, if you're interested in the physics of electron scattering, you can measure the structure factor of the solid. The other thing Hamish will tell you a bit about is high-order Laue zones, high-order scattering. If I look just in the 0, 0, 0 disk, the straight-through beam, and the sample's relatively thick, you see a lot of structure in there. That's very important crystallographic information. It gives you information about the 3D structure. It also is very useful for very accurately aligning my sample. I'm right on the 111 zone axis right now. I can tell that thing is centered as close as I can get by. This is just slightly off. That distance is tenths of a milliradian. Okay? Because remember, a typical Bragg angle, this is about 5 milliradians. You notice, so that's 5, that's probably, that's 5, that's 2.5, that's 2, that's 1, so we're a few tenths of a milliradian. So very accurate alignments. When we start talking about inelastic scattering tomorrow, we'll talk about the inelastic scattering. And remember we said the beam's coming in, it's interacting sample. Most of the stuff we talked about is elastic scattering. Well, what you don't know is that, go backwards here, when I have this pattern and I just put my sample in the microscope, we've got the elastic scattering, but also on top of it is all the inelastic scattering. Kikuchi lines, remember those? They're inelastic scattering. They're sitting in here. Now, if I have something called an energy filter, I can remove the inelastic scattering and then just look at the pure elastic scattering, okay? You can see what happens is we get rid of all the diffuse background here. That again gives us more information about the solid. There's actually information here and also valuable information here. I mentioned that structure in the diffraction and convergent beam patterns is very interesting, okay? If I look very closely at this, this is now a diffraction pattern where I only have 2 reflections excited. Notice the periodicity in those lines. I can show you that periodicity, mathematically, is due to a change in the thickness of the solid. If I take a line scan through here, this is what I see. If I measure the periodicity of those fringes, and I know the material that I'm looking at, I know the lattice parameter, I can tell you how thick that sample is. Okay? There's a methodology called, what's it called? Sorry. Oh, I've forgotten the name. Sorry. Back up. Okay. Pat Kelly developed it. Let me back up. Sorry, I have to back up. What he's been able to show is we can look at a diffraction pattern. We can look at the 0, beam and a diffracted beam. I know what that diffracting vector is. As the sample thickness changes, I go from a very thin sample to a very thick sample. The number of fringes that are here increases. The more fringes I have, the thicker the sample. So if I measure the number of fringes and their periodicity, I can measure the thickness of the crystalline area of the sample. Okay, there's the mathematics for it and the references for it are all here. Basically what you do is, we do a line scan through our diffraction pattern. We measure the fringe spacing. We do a plot of the deviation parameter as a function of 1 over z squared. We get a straight line. The slope of the line tells us the thickness. The slope of the line tells us the extinction distance, and the intercept tells us the thickness. Okay. There's still yet a third method on doing convergent beam diffraction. It's called CBED, positioned average convergent beam electron diffraction. And what you do here is you have a very small beam and you scan it and get an average diffraction pattern. You scan it over a small area. You get a certain thickness. You go to a different area and you look at the patterns as we go to different areas. They get thicker and thicker. We then, knowing the crystal structure, do a model of that. And from the model, you can tell the sample thickness again. So here's, for example, a experiment and a simulation. Experiment and a simulation, they can see they match. Now, what's good about measuring sample thickness with convergent beam patterns? Only works for crystalline materials. So if you have an amorphous sample, can you measure the thickness with convergent beam diffraction? No. Okay. There are other tricks you can use. We'll talk about them later. So, but what happens if you have a crystalline area with an amorphous layer on top and bottom? You still measure the thickness of the crystalline area, but remember you've got amorphous material on top and bottom. So what's the question you're asking? Is the question how thick is the crystalline area or how thick is the total sample? Those are two different questions. So, all right, I think we're about to the end and I'm getting talked out. That's the same. Oh, okay. Other stuff that Hamish is going to talk about, and I know it because I've seen his slides already. We looked at them over a few beers last night to make sure. He's going to talk a bit about higher order Laue zones, more information that you're going to get. So just give you a preview of what that is. Up to now, we've been just talking about diffraction right around the zero beam. If you drop your camera length way down, we see diffraction very far out in reciprocal space. Hamish will tell you a bit about that. Higher order Laue zones, I don't want to get his thunder, take away from it, but he'll tell you all about this. He'll also tell you about the symmetry that's possible in here. I'll give you a preview of this. We look at this diffraction pattern, and what do we see? What kind of symmetry do we see? I didn't hear somebody louder, I can't hear. 6, 3, who's picking 6, who's picking 3? Who's saying neither of those? What did you? 3, wrong. 6, wrong. I want you, if you look at this, it looks like either 3 or 6. And in fact, if you look at the triangle, you say, oh, it looks like 3. Let's look very closely at that inner circle. Look very closely at that inner circle, and this is what Hamish is going to talk about. This is the blow up of the center of that. I want you to look very closely. Is that threefold symmetric? The answer is no. Okay? Now, could you have seen it from this pattern? Nope. Can you see it from this? Not quite. But we can see it here in the higher order Laue zones that are in the 0, 0. You see a mirror plane right here. It's twofold symmetric. Okay? Close to threefold. And what's happening here? We've got a distortion of the lattice. Just slightly. If it was perfectly symmetric, this axis would look see these two? This one would look exactly like these two. So it's a very slight distortion, so very small changes in lattice parameters can be detected using this technique. And again, I'm going to leave that to Hamish because I'm getting tired of talking. Let's see. We can also use these Holtz lines to actually measure the accelerating voltage of the microscope. You turn a number and you say, oh, I want 300 kV, and you say, oh, it's 300 kV. No. It probably on most microscopes might be, instead of 300 kV, 298. Okay? And there's a reason for that because of the way they design some of the optics, and they design the systems to be compatible with electron loss spectroscopy. In the past, it used to be approximately 300 kV. Now it's 298 because they need 2 kV to do something else. But the very nice thing about these higher orders Laue zone slides, and this one is threefold symmetric, by the way. You notice this one is perfectly symmetric. You notice how these Holtz lines cross. If I change the accelerating voltage a little bit, I go from 113 to 100. And on some microscopes, you can tune the voltage very easily. You see how those lines change spacing, okay? So if you really need accurate measurements of your accelerating voltage, can you do it? Put in a known material, a known crystal. This happens to be silicon. We know what silicon is. We know the crystal structure of silicon. We can calculate this, and we can then match the accelerating voltage and determine exactly what it is. That's how I knew this was 113, by the way. We knew this was 100. We did the calculations. You got a pattern where these guys all collapse to a spot. And knowing that it's silicon, knowing the zone that we're in, we're able to say this is 113 kV, pretty precisely. All right, I think I'd like to end on, I think this is my last slide. Yes, it is. That's good. I can't talk anymore today. There's one of my very pet peeves. You know, pet peeve in the US is something that really gets me annoyed. The thing that gets me annoyed is a person will go up to an electron microscope and take a high resolution image. Okay, here's a high resolution image. We can see an image of a periodic image here. Very great. Then they will take a Fourier transform of that image and put this up and say, there's my diffraction pattern. A Fourier transform is not a diffraction pattern. Okay? Very important to remember that. A Fourier transform represents the periodicity that you see in an image. It's not crystallography. Is it related to the crystallography? Well, if the periodicity in your image is related to the crystal structure, yeah, it'll be related, but it's not a diffraction pattern. If you're missing, for example, you're out of focus or something, some of these diffraction spots, periodic images, will disappear. Okay. I've seen people try to do an image like this, then take this and say, well, I'm going to measure the lattice parameter of all my spots now. And they make a measurement on a Fourier transform. And all they're doing is measuring the periodicity of the image. So Fourier transforms are very useful tools. You saw how I use them to look at the astigmatism, because they show me the symmetry, the asymmetry. I showed you how the Fourier transform can tell you when the sample's drifting, if there's a distortion. Really powerful tools. They're very useful. Use them, but use them properly. All right, I'm done talking for today. I'm talked out. I need to let my voice take a break. So I think this is a good time to take a break, and I expect Hamish to be arriving shortly. Good. All right. Time for questions and a break, and a bio break, and whatever we're going to call it.